Hello, this is Silvia Mazzoni, and welcome to my first lecture on elementary structural dynamics. The focus of the lecture is an introduction to structural dynamics. Here's my slightly ambitious outline for the course. I actually think we do manage to cover all of these, and maybe it's a good idea to review them right now, so it'll remind me what it is that I'm supposed to cover in this course. So in the first lecture, I've broken them down by lectures, but I wouldn't count on that being so true because I wrote this a long time ago. So we're going to look at the fundamental objectives today and the types of loads and the method of discretization, whether it's a single degree of freedom system or multiple degree of freedom systems, and we're going to develop the famous equation of motion. The next lecture, we're going to review the fundamentals. I really want to kind of work with you guys on assembling a stiffness matrix and linear algebra, solving differential equations because our equation of motion is a differential equation, and start talking about Fourier series. I may move this lecture to a later time when it's a little bit more applicable to what we're doing. Maybe if we get the momentum going on the first part, I might just put this off until you really need it for later. Once we've done with the introductions and a review, we really get to the core of the matter right away. So this could even be in the second lecture. We talk about free vibration of single degree of freedom systems with and without damping. We're going to learn what all those terms mean and what each one of these different items represents and how we deal with it. We're going to look at the components of the equation of motion of dynamic systems. Actually, that we're going to look at in this lecture. We're going to look at the definition of the natural frequency or natural period of a system, the effects of gravity, how that influences a system, support excitation, and I think I'm going to actually hit that today in case of an earthquake. That's support excitation. Simple harmonic motion. We're going to learn what simple harmonic motion is. And then we're going to look at undamped free vibration and damped free vibration. Once we've done with the free vibration, now we start looking at forced vibration. So free vibration means the system is just shaking or vibrating without being subjected to a load. Forced vibration is being when it's subjected to a load. And then the response really depends on the type of loading. And we're going to talk about this today as an introduction. So the very first one that we're going to look at is harmonic loading. We're going to look at the response of harmonic loading. What is harmonic loading? Sinusoidal input. Harmonics are sines and cosines. So what is the response of a structure or a system to a sinusoidal input? We're going to look at undamped system and damped system. We're going to talk about resonant response, which is really exciting. That's kind of like the funnest part, I think, of the dynamics of a system. We're going to look at accelerometers and displacement meters, just how they work and how we can actually design them once we know enough. And then we're going to look at the options of vibration isolation and what damping does on a single degree of freedom system. The next section is going to look at periodic loading. So it's no longer just harmonic sines and cosines, but periodic loading, which are loads that repeat. Really giving you a view ahead on what's today, but a periodic loading is a type of load that repeats itself. It has a period. And of course, any periodic loading can be expressed in terms of a Fourier series, which is sines and cosines. So we're going to look at that and the Fourier series expression of the loading. And from that, we're going to compute the response using Fourier series in the load, and therefore we're going to get something like that in the response. And then we can also look at the exponential form of the Fourier series solution. That kind of makes it look a little bit cleaner. Which, if you're not familiar with what Fourier series are, I'm going to give you a couple links to it, but I highly recommend you go back to your math books or go to YouTube and learn about Fourier series. I think it's something definitely worth learning about and really getting familiar really well. It's really going to make things a little bit more complicated as we go through the class if you're not familiar with Fourier series. But it's not a very difficult concept, and it's actually a beautiful concept. Then we're going to look at the response to impulse loads, such as a shock, a load that's applied over a very short time. Why is that? Because then we're going to use that to then integrate it over time and pretend that, a random input is actually a sequence of shock loads. So it's kind of neat how we can do that in computing the response to these impulse loads and then to random functions. So we're going to look at learning what an impulse is. We're going to look at sine wave impulse, rectangular impulse, I think even triangular impulse. And then we're going to develop some response spectra for shock response spectra, which is just through an approximate analysis. From that, because we've built this tool, we're going to look at the response of general dynamic loading. And as you can see, each one of these bullet items leads you to the next one. We're going to look at the response to general dynamic loading through the time domain, so the Duhamel integral. We're going to learn and get familiar, and we're going to use the Duhamel integral for an undamped system. We're going to look at numerical evaluation and numerical methods, and the response of a damped system. From there, we've developed all the basic tools that we need, but we're still limiting ourselves to a single degree of freedom system. So then we're going to move on to a multiple degree of freedom system, MDOF, equation of motion, and the evaluation using matrices. What's really cool about matrices and vectors is that now we treat matrices and vectors almost like we deal with a scalar in a single degree of freedom system. So there's a lot of symmetry and beautiful symmetry in that, which means you got to get familiar with linear algebra. So that's the other topic that I highly recommend catching up on. We're going to look at the dynamic equilibrium conditions, axial force effects, elastic properties, mass properties, static condensation, which is really cool, and damping properties, which means is how do we assemble a stiffness, mass, and damping matrix? And then how do we reduce our stiffness matrix to match our mass matrix? Really cool stuff. That's one of my favorite topics because it's just pure math and linear algebra. Then we're going to, once we've really resolved in setting up the equation of motion, we're going to look at how we solve the equation of motion, pulling out our toolbox that we've already developed for the single degree of freedom system. So we're going to look at the undamped free vibration of a multiple degree of freedom system. What does that represent numerically, but then also physically? So we're going to have to go into mode shapes and flexibility formulations and orthogonality conditions. Things there get a little tricky, but I think if we're prepared and comfortable, I think we can get through that part of the chapter of the course as well. And then we're going to look at overall dynamic response, looking at superposition methods, normal coordinates, uncoupled equations. So we're going to look at modal and type of analyses, which is really what it leads to at the very end. But just how do we convert a multiple degree of freedom system into a simplified set of single degree of freedom systems? It's really cool, the math that comes in there and what we can do about it. Typically you can do that with linear systems, and sometimes we tend to extrapolate to be able to do this even to nonlinear systems. It may not be exact, but maybe it's accurate enough for what we're trying to do in engineering applications. So we're going to look into those. Of course, we're going to look at numerical methods, and to finish off, we're going to compute and define response spectra and modal analysis so that that sets you up for your following quarter. So this was a bit of an ambitious outline, but I think it was worth going through just so that you see how all the pieces really lead to each other. Right now, 99% of this may not make sense, but it'll be kind of fun at the end of this quarter. It'd be kind of cool to go back and put a checkbox as to which ones of these items you're now comfortable with. Lots of resources online. First one is www.google.com. But I'm a visual learner, so I like to go on YouTube. There's a lot of stuff on YouTube that's handy. It's really helpful to help you visualize some of the dynamic systems. I'm going to develop maybe a list of recommendations. There's two channels here that I think are interesting. One is the Smarter Everyday channel, which is this guy that just does these individual topic videos. And this one's really cool because it's a visualization of 4-year series. And then if you go to the Structural Dynamics channel, it's just by this fellow who's actually gone through Chopra's book one lecture at a time, and it's done a great job in teaching this course. So if maybe there's some topics that I don't make so clear here, or you would just really like to strengthen your knowledge, I highly recommend you go to the Structural Dynamics channel. All right, let's get started with going into structural dynamics. The very first question is, what is dynamics? Well, so in a dynamic system, the load varies with time, and the rate of loading affects the response. So for example, you could say that gravity is a load that could vary with time, or maybe as you're building a structure, the loads vary with time because you're building more and more. And so yes, you have a function of time, but then the second part is the rate of loading affecting the response. So if you're building your building and you slowly add on columns and beams and floors and walls, you're not really changing what is going on with the structure. But if you all of a sudden just dump a whole floor slab on top of your building, your system is actually going to oscillate and bring dynamics into the equation. So it's very important. That's really the difference is the load a function of time, and is the response affected by this time variability? So is the rate of loading important? So if it's loading really slowly at a very slow acceleration and velocity, then the load and the response represent a static problem. And that's really what we've dealt with all this time. So we're really bringing in is the time equation, or the time variable, into the equation. We've always just done, the force is equal to the stiffness times the deflection. Well, now we're going to add on to this terms. And that's exactly what we're going to do, actually. So you see it at the very bottom. It says the static system only has restoring forces. F equals k times delta here. So what does that mean? Well, that's this box right here. The restoring force, which is one of the components of a dynamic system, is the deformation or displacement dependent of a deformable body. So if you have a rigid body, you do not have restoring forces. You may have damping, and you may have inertial forces. So you may have damping and friction. You may have inertial forces in your masses. But what really matters to us is these deformations in our deformable body. And so that's our F equals K times delta in an elastic system. And then what we also have in static systems is external forces. But in this case, we've got time varying loads. The two additional terms that come into a dynamic system, it's something you're pretty familiar with. Especially when you think about a car, really. A car is almost the simplest representation of a dynamic system that we see all the time. You've got inertial forces, which are acceleration dependent, and inertial forces are the forces that want to keep you from moving. And then we've got damping forces, which are velocity dependent. What are damping forces? They're the shock absorbers in your car that they dissipate the energy. Inertial force is pretty much the weight of your vehicle that, you got to step on the accelerator to get it going. And the restoring forces are actually the springs in your suspension system. So if you really want to visualize a dynamic system, your car or motorcycle or even bicycle these days represents the simplest visualization of a dynamic system. So these additional forces here are really what defines our dynamic system. So the first place that we look at is the type of dynamic load. Different types of dynamic load determine different types of response. We're going to go through each one of these types of loads and compute what the response is for each one of these types. We've got periodic loads and non-periodic loads. Periodic loads have a pattern that repeats over time. It doesn't have to be a very clear pattern, but as long as it repeats itself over a certain amount of time. And non-periodic loads vary irregularly with time. And for each one of these two, we've got two different cases. So the first type of periodic loads are harmonic loads, so sinusoidal waves, sines and cosines. So for example, rotating machinery in a building, just something that just has a cycle that repeats, and it's pretty smooth and can be represented by a sine or cosine or a combination of the two. A complex Fourier series is one that is a complex shape that can be represented by a Fourier series, which is a summation of different sines and cosine functions with different amplitudes and different frequencies. And we're going to get into this, and you'll see it's kind of cool. You can use Fourier series to define any function that is periodic, that repeats itself in a certain amount of time. So you see here that this shape is rather strange, but it actually repeats over this period of time. And that's what we call the period, is that time in between cycles, which is the inverse of the frequency. What's an example of this? Propeller forces at a stern of a ship. Wave currents, where you got some big waves and smaller waves and tiny little waves and just lots of different waves depending on the different type of turbulence that you have. But there's still repeating loads when you have a wave, or it just keeps repeating itself after a certain amount of time, which just really means it's not a constant, it's not random, that keeps changing. But it doesn't necessarily have to be a smooth function. But smoother it is, the closer it is to a sine and cosine purely. And that just makes things a lot easier. But you'll see how we approach this with Fourier series and how we can improve this. The other type of loading is non-periodic loads. So they vary irregular with time, which is pretty much everything else. And within that, we've got two types of non-periodic loads. One are impulsive or impact loads. They're short duration. There's pretty much no oscillation. For example, a bomb blast or just an impact load, a truck crushing into your building or into another structure. So it's something that has a very short duration, and therefore it has a relatively definite response, because you've got a very short duration where you've got response that's a forced response, but then the rest of the time is just free vibration. So you hit something and then it goes wah, 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 and it just, if you have damping, it goes back to zero. These are important because that leads us to be able to solve the next problem, which is irregular loads. So irregular loads have long duration, and therefore the system oscillates. The best example, which is really what we're all here for, is earthquake shaking. So earthquake shaking, you can see it in the figure here. It's not well defined. You can't really easily represent it with sines and cosine functions. But guess what? You can represent it by a sequence of impact loads. And that's actually how we're going to solve the earthquake problem, or one of the ways that we can solve this problem. And so in summary, we've got two types of loads, periodic and non-periodic. And then within each one, we've got the basic functions. So for periodic, it's sine functions. For non-periodic, we've got impulse functions. And then anything that is made up of these, which is therefore the more complex shapes or irregular loads, can be solved once we know how to solve the first one of these cases. And that's what we're going to learn in this course. Just as we have different types of loads, which is kind of what I like to think of is on the right-hand side of the equation, which is your demand. I want to look at what's on the left-hand side of the equation. What is the system? Well, there's really two types of systems, not just structures, but we are focusing on structures here. But really, for systems, there's single degree of freedom systems and multiple degree of freedom systems. You guys are pretty familiar with this just from your structural analysis classes, but it's very important distinction for dynamics, and actually it gets really interesting and fun to see the relationship, the two kind of system. We're going to spend a lot of time on the single degree of freedom system, mainly because it forms the fundamentals, and it's going to give us the toolkits that we'll need to solve the multiple degree of freedom systems. Also, the best understanding of how phenomena works, or the math of it, is through single degree of freedom systems. Multiple degree of freedom systems you put into the computer, and that does a lot of the work, which is wonderful. But I think it's important to understand what it is that you expect from your structural analysis. So I really want to emphasize the importance of looking at what you think is basic, and it's never really going to be something. It's actually the single degree of freedom system is the fundamental knowledge for dynamics. Interestingly, too, most of the energy in the response of a system is typically in the fundamental mode or in the single degree of freedom representation. And then it gets a lot of fun whether we do it that way or we do it different modal superpositions and things. So, but trust me in the importance of getting to understand well the single degree of freedom system. Let's not get antsy to jump to the real world, because real world's overrated anyways. And then within those two systems, we've got two types. We've got undamped system and damped systems. What are those? Well, as I highlight at the bottom, damping represents energy dissipation, unconservative forces. So if you have an undamped system, your system is just going to keep on oscillating for a long time, actually forever, if you've got no energy dissipation. So best example of that, for example, is a pendulum, which is just a ball at the bottom of a rope. Or if you turn it over, it's a water tower. It's really cool to actually see water towers and how they really look like our representation of single degree of freedom systems, which is right here. Oftentimes in structural engineering, we like to draw them as cantilevers or as frames, but the simplest representation is a system that looks like this, where you've got a mass, a spring, which is your restoring forces, your dashpot right here, and your applied forces, and the mass is your inertia. And you'll see we're going to go through these in more details. Multiple degree of freedom systems are equivalent, or they go in parallel with single degree of freedom systems. There's undamped system. For example, an earthquake wing is a multiple degree of freedom system because it's one long beam, but then it's got individual masses at two different places. And you'll learn that where the mass is, that's what defines your degree of freedom or your dynamic degree of freedom. We're going to get into that when we look at multiple degree of freedom systems. So in this case, we're really just interested in designing this wing and how does it respond to having two masses distributed along the length of this cantilever beam. As you can imagine, it's different than if you had a single engine versus two engine versus three engines or n engines. So that is a multiple degree of freedom system. It's undamped because there really isn't much. We keep it elastic, and it's a response of this wing that acts like a cantilever. Oftentimes we represent multiple degree of freedom systems again with these springs and no dash pot in this case, but then we add a dash pot and that becomes a damped system. Damped multiple degree of freedom systems are things such as buildings. Here's a building, for example, that I got from the Taylor Devices website, where it actually has dampers, active dampers inside, not just the damping that comes from the material nonlinearities or the material damping itself, but you actually can put in additional dampers to reduce your deformations. Oftentimes in building frames, we represent multiple degree freedom systems using this graphic right here. And so this is just to show you how you can represent different systems either through the actual drawings or just through simplifications of these systems. So then that leads us to, we've got our system. What are we interested in? We're really interested in everything. Any quantity that we can get our hands on, we'll do something with it. So there's mainly three quantities. There's loads such as axial, shear, and bending stresses or forces. So the loads are when you've got elements that are brittle and you've got to design them to not exceed a certain axial load, maybe for buckling or a bending stress. Accelerations, more than for your structure, they're actually meant for the comfort of your occupants. You don't want to get your occupant seasick during a windstorm or even just basic wind in a really tall building. The velocity component also is part of the response of the components of your buildings, but it's also very much of a measure of how much energy is in the system. And deformations is something that we're interested in, especially now that we're doing ductile design. We want to estimate what are the damage levels and what is our damage index. Where are we with respect to the capacity or deformation capacity of your frames? So typically in structures, we're interested in the load deformation response, which is what you see here. You've got a system. What we're really interested in is what is the space shear as a function of lateral displacement. As we have an earthquake or even just some sort of loading, you've got a response that could be elastic or inelastic in your system. So some of the quantities that I described above are really used for the response of the structure itself. The accelerations and velocities are for the equipment. And importantly, deformations are also used for non-structural components, such as partition walls, such as glass. You really want to minimize your deformations because that could actually lead to very, very expensive problems with your non-structural system. Most important, for example, is your sprinkler system. You need to have an understanding of what the deformations are going to be in your system so that you can define and design flexible joints in your sprinkler system or HVAC system or other non-structural components in your structure. And also displacements are used for isolators. You want to estimate displacement so that you can design your base isolators, whether it's for equipment isolators or for your structure appropriately. And those are based on displacement capacities. Which then leads us to, okay, we've got the kinds of responses. Well, what type of response? Well, you can have a linear elastic response, which is shown here, which is we're going to address what happens in nonlinear systems, but those are handled numerically anyways, so it really makes the understanding of the math behind it a little bit overwhelming. But whenever I can, we're going to talk about where the divergence goes if you have an inelastic system. So you can have a linear elastic response. Linear means it's in a straight line. Elastic means that it reloads and unloads along the same line. The restoring force deformation response can be then defined by a simple and constant stiffness K. It could be a matrix, a stiffness matrix when you have a multiple degree of freedom system, but still that is a constant stiffness matrix or stiffness value. Then you go to nonlinear inelastic response, and now you've got a time, it's not really time dependent, it's a path dependent response. Energy is dissipated through hysteretic energy, not just through your viscous damping that you do elsewhere, but even just these cycles where it doesn't quite reload along the same path. Here's a nice sketch that I had drawn. Anything that is this area under the curve that isn't recovered, it means it's energy dissipation. And guess what? That's a really good thing. You want energy dissipation, whether it's through inelastic response, but you want controlled inelastic response versus uncontrolled in brittle systems. But if you don't have any energy dissipation, your system is going to keep on oscillating. And the energy dissipation actually reduces your deformation demands elsewhere. So it's really important to understand nonlinear response and being able to understand where you want to concentrate your, what we call hinges in your system. So you can't really live in denial of it, so you might as well take advantage of it. And I know it seems iterative, but I think it's important to focus on each one of these components is the different dynamic structural characteristics of your system. So the very first one that we're going to talk about is the mass. And mass is twofold. First of all, gravity acts on it. So you always have to put gravity into your equilibrium equation, okay? Make sure that you account for it. Sometimes it's going to fall out of the equation. You'll see that it's not always important, especially because it's not always in the direction of your loading anyways. But it's something that you always have to think about, okay, where is it with respect to this? And what really matters in dynamics is the inertia, which is the force that your system resists that it doesn't want to move. If Newton's second law says that if you want to move an object and change its momentum, which is mass times velocity, you have to apply a force to it, whether to bring it from 0 to something or from something to 0. So if you want to accelerate something or if you want to bring it to a stop, you need to bring in a force, and that's equal and opposite to your inertial force. What are the units of mass? It's mass units, which could be kilogram mass, or the force divided by acceleration. So it could be a force over length per time squared. And it's always important. I find that to be the easiest way. What I do is I take your weight and you divide it by g, depending on what kind of units you're in, and that gives you your mass values. Stiffness. Stiffness is something that we've talked about forever since we're mostly structural engineers, or even most engineers deal with stiffness. It's a property of a deformable body. As an undergraduate, I had rigid body dynamics, which was great because I had inertial forces and this and that, but it was rigid body dynamics, not deformable bodies. So we were missing that whole component. We talk about stiffness. Sometimes you can look at it as flexibility. One is the inverse of the other. It's a restoring force or a resisting force. It's pretty much how much force you have to apply to a system so that it will deform. And also it's the force that the system will resist to try to bring it back to its undeformed configuration. It could be elastic or inelastic. It could be linear or nonlinear. Elastic means that it reloads and unloads in the same path. Linear and nonlinear means that it's defined by a single line. You can have a nonlinear elastic system. I think shape memory alloys are like that. It unloads and reloads in the same path, but it doesn't have to be a straight line or a constant straight line. The units of stiffness are force per unit length. The third component is damping. This is something we talk about all the time, but quantifying is a pain because there's no direct way of measuring damping. So we're going to have to spend a whole lecture talking about the different ways that we can compute damping based on doing different experiments, which are really cool, but you can't just theoretically compute. Just as you can compute mass or stiffness, you can't just go straight in and compute damping. So what do? We define a model that's called mass and stiffness proportional damping. So that gives us a derivation for a damping matrix. As I've talked about before, damping is the main term in energy dissipation. What you keep in mind is inelastic systems can be represented by elastic systems, just put in more damping. Which means that if you're modeling your system with inelastic models, make sure you bring your damping in this case, because you're modeling it hysteretically, reduce the overall system damping. So maybe instead of doing 5% when you're doing nonlinear analysis of string structures, you actually go to 2% damping. Thermal effects can be accounted for with damping. Friction. In a reinforced concrete, it represents crack opening and closing. In steel structures, the friction at the connections, maybe your bolted connections that actually slide through and dissipate energy. If we design it carefully, that can actually be a good thing. As I said before, it's highly idealized. We don't really have a simple mathematical model for it. And so we idealize it through an equivalent viscous damper, which is just what's represented here as a dashpot. And it's almost like a catch-all for your analysis. The units are force divided by velocity, which is equal to force per length per unit time. Damping is a non-conservative force, which means it dissipates energy. There are different types of damping. So there's friction within the material itself. There's heat during repeated deformation. Fatigue is, so damping can be a good or a bad thing. It really depends on where you're at. It could be the micro cracks. It's caused by micro cracks in the concrete material, the friction at the steel connections, and friction with non-structural components as well. I think that's really an important field of study, is what is the effect of non-structural components such as partitions, glass, and things like that. How do they provide damping to your system? As I said, it's idealized by a linear viscous damper or dashpot. It's really most important during elastic response, because in elastic response, most of your damping is captured and modeled by your hysteretic model. And as I said, it can't be computed. It is just measured experimentally. You often do a system identification to kind of compute what the modes are, fundamental modes of a system, and what kind of damping you're dealing with once your building is built, actually. And what are the effects? It decreases the effects of resonance, so that's a really good thing, and we're going to talk about that. Resonance is when a system is excited at its natural frequency, so it would actually excite a long time. And there's a video at some point I will show you about a bridge that actually collapsed because the wind came in and hit the resonant frequency. And so nowadays you just need to add some dampers to these systems so that you're messing with the natural frequency of your system and you won't have collapse due to resonance. And it also does, as I said, an exponential decay of your response. And so here's two figures on the right where this is a slightly damped system, and so the response takes a long time to die out, while a highly damped system reduces in response a lot faster. And then in the end, this is really how we measure damping, is from these plots here through experimental testing. I've talked about the different mechanisms. Now with each one of those mechanisms, there's a force associated with it. So if you see in the top left-hand figure, you've got our idealization of a frame. And we can actually break it apart into three parts. There should actually be a fourth part, because one is the external forces, but then the internal forces are the ones associated with displacement, which is F sub S, which is our restoring force. So that's F sub S. Then we've got, based with velocity, you've got a damping force, which is represented here by this dashpot. And so here's your FD here. And then you've got your inertial forces that are associated with the mass and the acceleration, which is right here. So the inertial forces, as I said before, it's from Newton's second law, which defines a force to be equal to the change of momentum with a change in time. Now, when you've got a constant mass, then if this is the equation, the force is the change with time of the momentum, we drop off the mass part and we're left with mass times the change in velocity over time, which is equal to F equals ma, or F inertial is equal to mass times x double dot. Now this is the first time I bring in this double dot here, and that's how we represent the derivative of a function as a function of time. So acceleration is going to be x double dot, velocity is going to be x dot, and displacement is x. So this is displacement, velocity, and acceleration. So those are the derivative with respect to time. This could be a function of multivariables, but the dot at the very top represents a derivative with respect to time. I think you've seen these before in your classes. If you haven't, see me about it if you're not clear, but it's just a nice way of doing a convention. My main problem is that I can't get this easily to write in a Word document, so I always have to somehow fudge it or not. And then the other kind of forces are our external forces, which are applied to the system. So the inertial forces, as I said, and I started to say, is that it's a force that's needed to change the momentum of a system. So it resists motion, and you need a force to cause an object to change momentum, to start it to move or to stop it from moving. And there's our basic equation of F equals ma. The restoring force is a force that is resisting deformations and wants to bring the system back to the undeformed configuration. And so in a linear elastic system, is K times X, where K is the stiffness and X is the deformation. A damping force is a function of the rate of loading, and it's going to be computed as force is equal to damping coefficient times velocity. And so oftentimes you'll see it as C times X dot. And then the external forces, it really depends on the type of external force that you have. Now we've done all the components, what we're going to do is we're going to bring these different forces together into equilibrium. How do we define equilibrium? Well, you can state equilibrium in two ways. That the sum of all the forces is equal to 0, or that the sum of the internal forces is equal to the sum of the external forces. In the end, you can visualize it one way or the other. Because of just sign conventions and just taking one plus or minus the other. So here's an example. Set this aside. We're going to look at this later elsewhere. That's when you have excitation to an earthquake. So when you've got a system like this that has a force P applied to it, here it is deforming in this bottom figure A. Well, if we actually impose a displacement of our degree of freedom, because we have a single degree of freedom here, this mass can move to the right. So if this mass moves to the right, then what we have resisting are the inertial force. We have this mass, which is an internal force, is going to be our inertial force that's going to go to the left. We have our resisting force that's going to be a shear force in this direction that's due to these forces here. The force that is required to deform the columns and the beams too, okay? That's when things get interesting and complicated with structural analysis. And you also have a damping force that acts in the direction of the damper. Now, because we're only interested in this degree of freedom in the horizontal direction, we're going to do equilibrium just in that direction. Everything else in the other direction doesn't really matter. It's there, we have computed, but that's static equilibrium in the end. Or we can then just back calculate it once we've resolved our dynamic response. So there's two ways of writing equilibrium for this free body diagram. You can say that the sum of the forces is equal to 0. So P of T to the right is opposing the inertial force, the damping force, and the restoring force, but those are all going in the opposite direction of it. And so P of T minus F sub I minus F sub S minus F of T is equal to 0. Or you can say our external force P of T is equal and opposite to the internal forces that are resisting this force. So whichever way you want to write the equilibrium, sometimes I'll write it one way, sometimes I'll write it the other. It really depends on what I'm trying to achieve. But there's going to be your equilibrium forces right there. So this is a simple equation, and this is it. This is going to be the equation that defines our dynamic problem. Looks pretty simple. It kind of really is. So if we have this mass right here, and we're imposing a force here, we're going to do a free body diagram. And this picture comes right from the textbook. Then there's always two types of free body diagrams. There's the one here that shows the object, but then you have to remember to bring in the inertial force as well. See, here's gravity, but gravity cancels each other, so we don't worry about it, and we're really interested in this degree of freedom. Okay, we do have inertia in the other direction, but it's reacted by the wheels and the supports here. So we don't have to worry about the inertia in the vertical direction for this case. And so this is degree of freedom 1 and only a simple single degree of freedom. So let's do equilibrium. So we've got the inertial force, mu double dot, plus the damping, plus the spring force is equal to the applied force. Well, let's convert that. The damping force is equal to our damping coefficient, which we have to figure out, and we have to define it for our system. And we'll go through and I'll show you how we're going to do that when we solve these problems. And then we've got, for an elastic system, K times U. This is the case where this is just elastic, but sometimes you might want to keep it more general and you don't have to assume an elastic system. This here is now what we call the equation of motion. And guess what? The equation of motion is a differential equation. In this case, there is no derivative with respect to time or other variables, so it is just a very simple ordinary differential equation. And we're going to have to solve this ordinary differential equation. It's a second order differential because we've got the second derivative of the displacement. It's one equation and we're solving for one unknown, so this can actually be solved for, because once you've got u dot and u double dot are derivatives and therefore derived from u. So it's a single degree of freedom system, one equation, one unknown, we can solve it. And that is the focus of this course. How do we solve this equation of motion? This is the general case, but since we're staying elastic, this is the simplest form of the equation of motion. Just wait, it's going to look really cool when we go multiple degree of freedom system. It's going to look just like this, but we're going to have vectors and matrices instead of scalars. This is a single degree of freedom system, so it's just a single scalar variable of u. What's really important to keep in mind, and if you remember this from your differential equation class, the solution is fully dependent on this external force. And that's what we're going to spend the quarter here trying to figure out the solution to different types of input. A very important consideration that I want to highlight early on is what happens when we have earthquake excitation. If you go to the previous figure, which I can't do right now, we actually had a force acting on here. Well, when you have an earthquake, you don't. It's not like you have a higher being there pulling you to the side. What is actually happening is the support is being excited. It's the ground that is moving. And the ground is displacing and has a displacement, a velocity, and an acceleration. And as the ground moves, this whole thing is going to move with it. So if we have a rigid system, so if this is our original model, okay, and we have a rigid block and the ground moves, the block is just going to move with the ground and not respond, okay? If it was attached to the ground, it would just move with it. If it had friction, then you may actually have a response here because you've got inertial forces that are opposing this, and you have friction forces or your dissipative forces, okay? But we have an additional term in our systems, which is the deformation and deflection of the structure as well, because we have a deformable body. And so you can see it here where you have your original figure. This was your original structure. I made it a little bit fatter and wider. And so as the system moves, or as the ground moves to the right, your frame now has moved to the right as well. Okay? If it was rigid, this is what it would look like. But because it's deforming, this is your new deformed structure. I really ruined it here, but pretty much this is your deformed configuration. I'm just trying to not worry too much about the angles there, okay? That really depends on the boundary conditions. So what's happened to your system? It has moved over to the right a certain amount, so the ground has moved this way, but then you've got this additional u, so this is u ground right there, but now you've got u, which is the deformation of your system, and therefore you have a total displacement of your mass, because your mass is up here, it's not down at the joint. If your mass was at the base, then it would only be looking at U ground. But because it's on top of a flexible system, now the total deflection of your mass is going to be U total, which is U of the ground plus the deformation, okay? Which is what I'm showing right here. This is ground and this is deformation. The derivative and the second derivative of that is also the case. So the second derivative, or the total acceleration of your mass, is equal to the total acceleration, or the ground acceleration, which is how we typically deal with earthquakes. We actually look at ground acceleration. We don't look at displacement, because we can't measure displacements. We can measure accelerations, plus the acceleration due to your deformations, okay? Which is just a second derivative. This is really important, because there's a couple of things to keep in mind with what's going on with our physical system. And I really want to make sure that you guys understand here that the inertial force is resisting the total acceleration of your mass. Until now, we only thought about the mass times the second derivative of U. But that's because we didn't have a ground that was moving. It was a fixed base, which I'll show you at the very end how we deal with this. But when you have a ground moving, your total acceleration of your system is actually the ground acceleration plus your U double dot, okay? Which is easy, and that's fine. So we've solved for F sub I. We've got to do our equilibrium equation right here, right? So we know what F sub I is. Now, what about the damping and the spring? Well, guess what? Damping and the restoring force are really interested in deformation. They're not interested in the rigid body, okay? If we had friction, that'd be a different story, okay? But this is actually connected to the ground. And so our damping force and our spring force are actually a function of U. You know, not U total, but just U of the deformations. And so we're going to plug these three relationships, and you know, for a linear elastic case, this is what you have. We're going to take these three quantities and plug them into our equilibrium. So we start off with the inertial force plus the damping force plus the spring force. Hey, there's no external force. If there also happens to be an external force, you put that right in. Okay, man, talk about bad luck. So we got the sum of the forces is equal to 0. So now let's plug in, first, let's just deal with the inertial force. So it's mass times the total acceleration, which really is equal to mass times the deformation plus the ground acceleration plus the damping and the spring are equal to 0. What I'm going to do now is I'm going to split this up into two components. I'm going to take the deformation, keep it on one side, and the ground, put it on the other side of the equation. Why is that? Because this value I know. This is known. Okay, this is like our external force. So we're going to move it to the right-hand side of the equation. So what happens to our left-hand side of the equation? We're left with M times U double dot, which is right here. Now we're going to plug in for the damping CU dot plus F sub S as a function of U, which is just in the elastic's case will be K times U. Well, guess what? This is exactly the same equation as we had before on the left-hand side, but on the right-hand side, we've got a term here, which is negative. Very important. Don't forget that negative. I always forget the negative. Times the mass times the ground acceleration as a function of time. And now we can solve this equation because this looks like just any other equation that we have. And it's almost like saying that we have an effective earthquake force. When you have a system that looks like this, with no external forces, you can replace it by a system that looks just like your previous systems. Now you don't have anything at the ground anymore, it's fixed ground, but you have an effective force equal to the negative times the mass times the ground acceleration as a function of time, and you have that value. And so an earthquake ground motion, and you'll see this, and I want you to really understand this because this is going to be in your exams. You're going to have homework problems with these kinds of questions, and they're not going to be as straightforward as this, but I want you to understand the concept And really the main concept is all here. If you understand how you break this up, the rest is just math. So inertial force is the only one that it's not just about deformations, but it's total acceleration. And so it's interesting because when you go down the line and you start doing your analysis in open Cs and whatever, perform or different models, the output is, hey, what do you want? Do you want your relative acceleration, which is the second derivative of this displacement, or do you want your total acceleration? And you actually have to tell it which one of the two, and they're two very different concepts. So I wanted to get this out of the way only because this is important and there's nothing hard. It's just a little tricky, and you just got to make sure you understand what we do when we've got earthquake excitation. Okay, so I want you to look at this, spend a little bit of time on this, review it, and make sure that you understand what it is that I'm doing and why I'm doing it. And this is why I spent a bit of time on this. Now, that was pretty much it for single degree of freedom systems. The challenge, as I said before, is going to be solving them for the different cases of input forces. And that brings us to multiple degree of freedom systems. We approach multiple degree of freedom systems in exactly the same way that we approach single degree of freedom systems. It brings in a little bit more of the analysis, structural analysis, and how to assemble the different matrices, and I'll show you here. But I want to give you a taste of this today to just make sure for completeness that I've shown you the concept, mainly what the final equation is that's in the next page, so that when we come back to this, or you can actually understand why it's so important to understand what we're doing with single degree of freedom systems, because multiple degree of freedom systems just require a little bit more structural analysis, but not really more structural dynamics. Actually, yeah, when you get into modes and mode shapes, that gets a lot of fun too. So, okay, so here's our multiple degree of freedom system. The easiest one is to represent it with masses and springs and dashpots. We've got two masses, mass 1 and mass 2. Now, as I said before, each mass here, they're not connected by rigid links. If they were connected by rigid links, then they could be represented by a single degree of freedom, okay? In the previous example of a frame, we actually assumed that the beam was actually rigid so that the masses at the two ends of our beam actually moved together, and that's why it was a single degree of freedom system. Here, they're connected by a spring and a dashpot, so they move independently. So we're going to start labeling things, and this is really important that you get familiar with labels and directions and forces and get comfortable with equilibrium. Very important to always do a free body diagram as you go through your systems to make your life correct in terms of sign conventions, okay? And I know this is going to be something that we're going to be visiting again and again. So we've got these two masses, therefore we got 2 degrees of freedom. Mass 1 has degree of freedom 1, and mass 2 has degree of freedom 2. We're going to label them x1 and x2. Now, in this example, we've got a number of different springs and dashpots. So we have a rigid wall, very important, and then we've got a spring here between this mass and the wall, and a spring here that connects the two masses, okay? And they've got different spring coefficients, of course, because that would be too easy. And the same thing with the dashpot, okay? Makes it a lot easier because we can solve for K's, then we can do the same thing with our dashpots. And then we have an external force, F0. And so this force is only applied at this degree of freedom and not at there's no forces applied here. You may see examples where you then actually may have a force at this degree of freedom, okay? But we don't in this example. So we're going to do a free body diagram for each one of these masses, okay? I drew these backwards. So this is x2, and this here is x1, okay? So one is to the left of the other. I switch places for them. So let's do equilibrium. It's always easier to do equilibrium from starting one end and moving forward to the other, okay? So let's look at mass 2. We've got an external force, F, so here it is. Then we've got the inertial force due to this mass, which is internally right here. Then we've got a spring and a spring, okay? and a dashpot. And we're going to figure out what these two forces are. But right now we're going to put them Fs2 and Fd2. If we look at this mass over here, we're going to have the same equal and opposite forces that were coming in from there. And so we got Fs2 and Fd2 acting here and here. And then at the other side, I have K1 and C1. So I have Fs1 and Fd1. I have no external forces applied at this mass mode, okay? So let's break these down and see how we define them. So the inertial mass, or the inertial forces, F inertial 1 and 2, are going to be equal to mass 1 times x double dot 1. All right, there's no ground acceleration here, so it's just the value. We can put away what we went through with the earthquake analysis. So it's m1 times x double dot sub 1, and the inertial for the second mass is m2 x double dot 2. Okay, mass is the one that makes things complicated in some cases, but in this case it's actually the easiest degree of freedom. Now let's look at our damping and resisting forces. Let's do the damping force here. Okay, actually let's look at the resisting force, because then the damping is the same. So the force here, K1, is equal to, because this is fixed here, it's pretty much the spring gets elongated along with x1. So and it's very important to keep track of it, and it's as x1 moves to the right, the force is going to be going to the left. And so we say Fs1 equals to K1 times x1. And just by symmetry, that's the same thing for the damping force. Now let's look at force 2. Okay, and I drew that. I was actually over here. This is Fs1 and Fd1. Now, what are these guys that are the forces inside this system right here? Well, these forces here for both damping and resisting force are relative. And so what you want to do is, and you can see here, F sub S2 is equal to K2 times, it's an elastic system, x2 minus x1. So what this is saying is if x2 moves to the right, so if they're the same, it means they're moving together. Therefore, there's no force in my spring. If x2 is bigger than x1, so it's moving to the right more than it's moving to the right over here, that means my spring is elongated, and therefore it is pulling here and here. And that's why I am drawing it that way here. And because I'm drawing it like this, I'm defining it as K2 times x2 minus x1. If I assume the opposite, if I assume that x1 is, and you don't really have to assume it, because then the sign comes off anyways. Because if in actuality x2 is smaller than x1, then this term becomes negative, which means that the spring is actually pushing. And so it works either way. You decide what your sign convention is. And based on keeping this as a positive value, then you're drawing it in this direction. You can go the other way if you're more comfortable with doing x1 minus x2. And if x1 minus x2, then that's going to give you forces that would act in this direction. So here you'll be plotting it this way. And then your signs would work out with that equilibrium. So it doesn't matter which way you choose. And sometimes I choose one, sometimes I choose the other. It doesn't really matter, as long as you then draw your force in the right direction. This is really important later on when you get into flexural members and looking at things like shear and bending. It gets a little bit complicated, but if you deal with the right sign convention, then everything kind of falls through properly. Okay? So you're welcome to go through this a little bit, maybe pause and go through this concept, but you can actually put it the other way, and then your forces will be in the opposite direction. Okay, so I've defined all my forces, so now let's do equilibrium. I've got 2 degrees of freedom, and therefore I got 2 equilibriums, one here and 1 here. So let's do equilibrium of my two free body diagrams. And you're going to have as many free body diagrams as you have mass degrees of freedom, okay? And therefore dynamic degrees of freedom. So I'm going to say that F inertial 2 plus F damping 2, which are in these, all these are in this direction, are equal and opposite to F0. So I'm going to put F0 on the right hand side, okay? What goes to the left is equal to what goes on the right, or vice versa, one minus the other. Down here, what's going on with this equilibrium? Now this gets interesting, okay? At mass 1, what do we have? And these are all internal forces, so they all have to go on the same sign. But, you know, we're going to take this as positive. Therefore, we've got, and actually, it doesn't matter because I'm actually taking this as positive, it seems. But because you're setting it equal to 0, and as long as you pick 1 and you're consistent, then you're fine. So F1, F sub S1 plus F of D1 plus F inertia 1 minus, so these are all positive, and then minus the negative, which is FD2 and F sub S2 are equal to 0. So now we got these two equations, and what are unknowns? Our unknowns are x1 and x2. Then from there we get x1 dot, x1 double dot, and so on. Okay, and so we got two equations for two unknowns. Well, let's take these guys here and plug them into these two equations. So we got F inertial 2, and so it's m2x2 double dot plus c times, because it's this right here, fd2, x2 dot minus x1 dot plus k2 times x2 minus x1 is equal to f naught. The other equation is for the other degree of freedom, which is the second equation here. So F inertial 1 plus F damping 1 minus F damping 2 plus F resisting 1 minus F resisting 2 is equal to 0. Now you'll see that we can actually group terms instead in terms of x1 and x2. We want to group them because it just kind of works out a little bit cleaner that way. What we're going to do is m, and we're going to put this is equation 1 and this is equation 2. I had done all these a little bit backwards last time, and I should have fixed this right now. But I've got m2, so down here, which is the one that's got the most term, m1 x1 double dot, so that stays. Now I've got c1 x dot 1 and minus negative c2 x dot 1. So it's actually c2 plus c1, or c1 plus c2 times x dot 1. Now the x2 dot is a single term here, so it's minus c2 x2 dot. And then by symmetry, we're going to do the x1 terms here. So it's k1 plus k2 times x1 minus k2 times x2 is equal to 0. All right, it's a little bit tedious, but it's actually not so bad, okay? Now the other equation up here, we do the same thing in the grouping and regrouping. So we got m2 x2 double dot. Now x1, there's only one term here, so it's minus c2 x1. x2 is plus c2 x2 dot. And then same thing with the x2 and x1 is going to be minus k2 and plus k2 here. So here's our equation, two equations of motion. Remember, we've got two equations and we solve for the two unknowns. Okay. So now I'm going to just go to the next slide, and I'm going to just take this back with me, and we're going to keep going with this work. Okay, so we've got our multiple degree of freedom system. This is the equation we just derived. Well, now let's get into some fun stuff, because look at this. We can turn these into vectors. So if these are our vectors, okay, and we're going to make a vector. So for example, x1, x vector is equal to x1, x2. Okay, and therefore x dot vector is going to be x1 dot, x2 dot. Okay, so now let's group them. Mass, these are x1 and x2. So if we pull them out into a vector, what we're going to do is we're going to have a matrix. M1 plus, what's the term in front of x2 double dot here? There is none, so it's going to be 0. And same thing for the equation below. It's pretty much 0 times x1 double dot. And so that's why you have this representation here is this equation here. Okay? Now the second one, as you can see, we've got x1 and x2 here. And so we're going to turn these coefficients into a matrix. So we got C1 plus C2 times x1 minus C2 times x2. Right? That's how we do matrix multiplication. This row times this column. And then down here is going to be this row times this column. And that makes sense. Down here we got minus C2 and plus C2. Same thing with the mass matrix. And you guys have done this before for just assembling, just this part of your static equilibrium. But now we've got K1 plus K2 times X1 minus K2 times X2. So we got K1, K2 minus K2 times, so it's this row by this column. And then here we got minus K2, so we got this row times this column. And then F, one of these should have had F0. Okay, and so here I have a vector of F0 and 0. So there it is. Now look at how cool this is. If this is our x vector, x dot vector, and x double dot vector, x1 dot vector, and the velocity and acceleration and displacement vectors, then we can write those in terms of a mass matrix, damping matrix, and stiffness matrix. And we've got mx double dot plus cx dot plus kx equals to f naught. And these have got all underlines below. It means they're either matrices or vectors, okay? If you want, I can sometimes write these as vectors just to kind of improve. And guess what? That equation of motion looks exactly like equation of motion that we had for a single degree of freedom system. Mx double dot, but now we've got matrices and vectors. So if we can solve this for this top single degree of freedom system, it's really going to give us a lot of information on how to solve a problem with multiple degree of freedom systems. This was a little bit complicated here, but we're going to be doing enough exercises and homeworks to really get familiar with this. Maybe it's an opportunity to go back to statics and structural analysis and get familiar with it. If not, if you haven't done this before, one is come and see me. Two is look up a YouTube video. Maybe look for a couple of YouTube videos so you have a little bit more knowledge, and then we can talk about having a little bit better understanding of it. I hope that just going through this and this math here doesn't quite scare you off. If it scares you off, then please come and talk to me because we're going to be doing a lot of math in this course. And it's actually not so bad as long as you can catch the fundamentals of what we're doing. So I'd rather help you with it early on than later. And so now that I've made it complicated, I'm going to go back to the simple cases, all right? Now, here's an example, and these are from the textbook. I believe they're actually homework problems, where you got more springs than you thought you did in the simple example. So how many degrees of freedom do we have? Well, guess what? All three of these cases are single degree of freedom systems. I mean, just because we got stiffnesses, it doesn't matter. We got to look at our masses and how independent our masses are. Well, we've got only one mass in each case, and so right now it's simple, a single degree of freedom system. What happens is we've got to solve for the equivalent or effective stiffness. Well, look at this. Doesn't this look familiar? In the first case, we've got springs in parallel. In the second case, we've got springs in series. In the third case, we've got springs in parallel in series with another spring. And so what it really comes down to is figuring out what our effective stiffness is for these cases. And if you remember, we've done this before. in adding stiffnesses and flexibilities, and I think it's just a matter of understanding what is what, okay? In some cases, forces are additive. In some cases, deformations are additive. So let's look at each case independently. So the very first case where we got springs in parallel, what does this tell us? That if you look at this term right here, okay, and even the free body diagram actually, okay, so just pretty much the schematic here. When you've got springs in parallel, the two springs have the same force, or do they have the same deformation? And that's the question that you've got to ask yourself. So when they're in parallel, you can see here, you got this little block here, and this guy's going to move to the right, and it's going to take those two springs along with it. So when the springs are in parallel, they have the same deformation and different forces. One spring is going to be easier than the other to pull if they have different spring coefficients. And so what you do is you do equilibrium based on that. So the force here on the right is equal to the sum of these two forces, okay? So they have the same deformation and the forces are additive. And the deformation is the same for the two of them. So F sub S is equal to K1 plus K2 times U. So that's our equilibrium equation, or just equilibrium of forces. Therefore, the effective stiffness is going to be the force divided by the deflection. That's how we define stiffness. And so K effective is equal to K1 plus K2. So our equilibrium equation, don't forget that we've got a mass here, okay? So now this is simple equilibrium of the springs, but now we've got an inertial force here, and we've got K1 F of K2 and P of T. But remember that because these share the same deflection, we can now say I've got an inertial force in this direction, my P of T is here, and then here I've got Fk effective. And therefore my equilibrium is going to be F inertia, which is mu double dot, plus, I have no damping here, K effective times U equals P of T, where K effective is equal to K1 plus K2. Guess what? This equation is going to carry across in all three cases, because it doesn't matter once we get to this second free body diagram. So then if we look at the second case, now these two springs have the same force in them and the deflections add up. So if we do equilibrium of this force is equal to the total resisting force. Okay, so this is F sub S is equal to deflection 1 plus deflection 2, right? And therefore U total is equal to U of U1 plus U2. And F sub S in each one is equal to K1 times U1, and F sub S is equal to K2 times U2. Do we set the two equal to each other? No, we just kind of solve for the total F. Okay, and this is when you've got to do inverses, okay? So instead of doing the force, we compute the deflection, okay? So F equals K effective times U, where U is the sum of U1 plus U2. So you've got these two relationships here, and then if you've got to solve for U1 and U2 in those, then you say F sub S over K effective, which is what we're trying to solve for, is equal to F sub S over K1, which is U1, and so this is U is equal to U1 plus U2, And so F sub S cancels out on all of them. So we got 1 over K sub effective equals to 1 over K1 plus 1 over K2. And therefore the K effective is equal to, is pretty much 1 over K effective, is this equation right here, which you then have to simplify and turn over. K effective is equal to K1 times K2 over K1 plus K2, okay? This is pretty much the equivalent stiffness in series, in springs in series, okay? This is something you have to go through. I'm pretty sure you must have gone through this in the past. You do the same thing with resistors in circuits. This was, for me, it was a long, long time ago. For you guys, it may not be as much of a long time ago. But again, I highly recommend that you go through this exercise to really understand what it is that we're doing in each step. Now, the third one is really the test of it. But now we're going to just kind of go and make things simple. What we want to do is you first turn one system into the other and just do them gradually. So what we're going to first do, so here's the schematic. First, we're going to convert these into an equivalent spring. And we know because they're in parallel, the effective stiffness is going to be K1 plus K2. And now these two together in series, the effective is going to be K effective times K3 over K effective, the first K effective, okay, this K effective, plus K3. But this is actually K1 plus K2, which we had it here. So our K effective is going to be equal to K1 plus K2 times K3, right? I'm just plugging into here, over K1 plus K2 plus K3. And every time is going to be different. Now, the question I have for you is, what if I have a system that has springs on this side and springs on this side, and I have an applied force? Are these in parallel or are these in series? And that's what I want you to think about, okay? And if you kind of go by process of elimination that it's one or the other, or ask the question, do they share the force or do they share the deformations? Is this going into here or is this going into here? That's really the question. Okay, so these are just simple problems that kind of get tedious and complicated, but it's a really good way of just kind of getting yourself familiar with what you're doing with computing springs or effective springs, and also the understanding that this is still a single degree of freedom system. So this is still an SDOF. All of them, even if I have a whole bunch of springs. What does that tell me as a structural engineer? What do those springs represent? They represent beams and columns. And I've got to figure out how to combine the resistance and the stiffness components of the beams and columns. Maybe I've got beams and columns coming in from the left, from the top, and different directions, okay? So this is almost it's supposed to be simpler than beams and columns, but it gets a little bit harder to visualize. But that's the example that I'm going to give you next, or after the next one, on how we deal with frame elements, which then get a little bit more confusing because these are simple Ks. Now we're going to be dealing with EIs over L's cubes and EIs over L squareds and terms like that. Okay? And there it is. So when we're dealing with beams and columns, very important that you go back to your fundamental of structural analysis and you find the table that corresponds to these figures that I've given you right here. These are statically indeterminate systems, and these form the fundamental values that you really need, and it's all you need to compute all your stiffness coefficients, okay? What I have here is your stiffness coefficient is, the definition of a stiffness coefficient is the force at degree of freedom I, so K sub ij is the force at degree of freedom I due to a unit deformation at degree of freedom. There shouldn't be no j, it should be degree of freedom j, while keeping all the other degrees of freedom equal to 0. So here's an example, and these are the two basic systems, okay? This is fixed at one end and pinned at the other, and this is fixed, okay? Because most of the time we're applying unit displacements or unit rotations, and so these are the two fundamentals that you need. Then everything else here is extras that can help you to just kind of make things faster and easier. And what I did is, on the bottom left, I gave you what I got online that gives you for most cases. I hope that these look familiar to you guys. And what I've done from those is I've selected the most important ones. I believe this is really the one that you should memorize most comfortably. And then in some of the exercises, we're also looking at this one. This one here can be derived from up here, just like this one can be derived from here, but it's just easier to memorize or learn those. I recommend that you memorize these terms through use. You will end up memorizing them, or always just write them down and have them in your cheat sheet whenever you do some sort of exams or something where you can carry those values with you. At some point you kind of start getting familiar because they're not that different, because K sub ij is equal to K sub ji. The stiffness matrix is symmetric. So look at this. We got 6EI over L squared and 6EI over L squared. So those are the ones that you really need to learn. Because this is symmetric, these two values are the same. And same with this 6EI over L squared. So what you're left with are 12EI over L cubed, 6EI over L squared, and then you got 2 and 4 EI over L. And so it's tricky to remember the L's, but then it's like, oh wait, this is a moment due to a rotation, this is a rotation due to a displacement or to a force, and vice versa, and then this is the displacement due to a force. So it kind of works out in recognizing what the degrees of freedom are. Okay, these are very important because these are the K's that you'll need in assembling a stiffness matrix. In a multiple degree of freedom system, so you're not going to need these right away, but some of these are important. So for example, in many cases when we're dealing with single degree of freedom systems, we're going to be looking at cantilevers. So it's very important to know what is the K term for a cantilever. What is the force corresponding to a unit displacement, or vice versa, what is the displacement corresponding to a unit force? So here's a relationship between force and displacement. The K represents a unit displacement, so it's really the inversion of the delta here. Okay, so I just kind of wrote these on the right hand side for you. So this is a simply supported beam with the load in the middle, and that gives you what the deflection is, and therefore if you have a unit displacement in the middle, this is the force that is needed for that. So you can go vice versa on these and invert them. As I said, it's the force at the degree of freedom due to a unit deformation, or the inverse of it is the deformation due to a unit force. Okay, so one's flexibility and one is stiffness. Important that you get familiar with what each one represents. And so this graphic here, I recommend you sit and you maybe spend time understanding what these different quantities represent. I will go back to this when we do multiple degree of freedom systems. The way these are derived is using the principle of virtual work, probably principle of virtual displacements. I am not going down that path. And so these are values that you want to just memorize and maybe go back and figure out how these values came about. It's actually really cool on how they're done. So I recommend it. It's not so hard because the over constraining is not that many degrees of freedom, so it can actually be done relatively easy. But these are the terms that you're going to refer to as you go through homeworks and exercises and through the class. So here's my example that are actually problems from the textbook. So now what I want to know is, what is my equation of motion, but really what is my stiffness? So the question is, what is K here? It's undamped, so once you have K, then you've got the mass and inertia. Now, what you want to first keep track of, this is weight, so the mass is going to be the weight divided by G. Now, look at this. This is, you know, a mass on top of a beam. So if this degree of freedom is my degree of freedom to the right, no, that's not really what I'm interested in, right? It's not going to slide. So my degree of freedom is actually in the vertical direction, okay? And it's actually shown in this figure here. There's U here, there's U here, and there's U here. All right, so what you want to do is you want to draw the deformed shape and impose a unit displacement in the degree of freedom that you're interested in, and you say, okay, what is the force that is needed to impose that unit displacement while keeping all other degrees of freedom 0? Well, I don't have any other degrees of freedom here, and that's why I'm looking at a simplified model here where I've got the cantilever. So here's my cantilever, and not cantilever, simply supported beam. It's going to deflect here by a unit displacement. Well, if we go back to, and I'm cheating and I'm putting here, that delta is equal to PL cubed over 48 EI. Therefore, K is equal to, setting this equal to 1, and what is P? So P is equal to, K is equal to 48 EI over L cubed times delta, which is 1. So K is 48 EI over L cubed. Okay? Second case, I have a cantilever. My degree of freedom is downward. So now this is delta. And if I look here, delta is equal to PL cubed over 3 EI. Therefore, K, which is equal to P of delta equal to 1, is equal to 3 EI over L cubed. Okay, well, those were easy ones to do. Now we got to do the last one, which is a little bit more complicated because I do not have this diagram. You can look this up, and I bet if you go online you can find out what is the deflection at that degree of freedom. But I'm actually going to sketch it out. So I have fixed and fixed. So what this is going to look like is difficult for me to draw. Something like this, where this is 0 slope here. And what is this deflection? Well, this guy here, where this slope is 0 here, is really half of this beam. Okay? And I know that the deflection, the force that it requires to push it down, is equal to 12 EI over L cubed. Okay? And so, but this is L, and here, this is actually L over 2. So I require 12 EI over L cubed, and this is 12 EI over L cubed, but this is actually L equals to L over 2. And so if we plug that in, so it becomes, I have very little room here. And so if L equals to L over 2, then 2, because I've got the total F, which is equal to K, is equal to 24 EI over L over 2 cubed. well, 2 cubed is 8, right? And then now that's going to be up to the front. So 24 times 8 is equal to 8 per 8, 64. 8 times 16, 17, 18, 19, 20, 21, 22. 224. Wait, what am I doing? It's not 6 times 4, it's 8 times 4. Okay, so we have 24 times 8. So 8 times 4 is 32. 8 times 2 is 16, 17, 18, 19. And so K is equal to F is 192 EI over L cubed. I can't write anymore. Here's one stiffness, here's the other stiffness, and here's a third problem. Okay, so what I want you to do, I think it'd be great to go through these. This is basic structural analysis still. It's kind of a review, but I know a lot of people haven't done this type of exercise, but it's really important to go through and review what I did in each step here. Try this on your own and see if you get the same answer. If you don't, try different ways and see if you can get to the right answer. This 192 EI over L cubed is something you could even find in the textbooks, but I thought it would be a good opportunity to kind of just show you how we can compute it if we don't have it from a table. Okay, so I hope that this was a helpful exercise in just trying to go through this and not making it seem like such a simple concept.